aside from the toolset lets you lex and parse and talk to the RPC service. We wrote a few other tools that actually help you in locating the IDLs and the binaries that define such RPC services. So we have one script that will recursively go through a directory and give you IDL and IDB generation. We have some PyDebug scripts. PyDebug's a Python-based scriptable x86 debugger. So basically you'll be able to, if you happen to be developing anything with relation to RPC and you want to deal with debugging it, we have some PyDebug scripts that hook into RPC-RT4, dump format strings, and kind of help you. It's more for developing than auditing. Some tools for binary name pipe extraction that basically uses IDAPRO to pull out some of the name pipes that you will need to be able to talk to some of these services, and some symbol inference stuff. And Cody's going to go through some of these. Is this you? That's you. Well, the first tool is, like I said, it will recursively go through a directory, find any execs or DLLs that import RPC-RT4, then it'll go through and find any of the imports that match RPC server functions specifically. It will then launch IDAPRO, which is a disassembler, and it will run the mIDA plugin, so it'll provide you with IDLs and IDBs for any discovered modules. So you can essentially have, say you install some product and you want to know if it has any RPC, you can run this script on the program files directory for it, and it will tell you any services that will define RPC. And then you can go through and see if any are named pipes or TCP. You have all the IDBs, which are the files that IDA saves. It's all done in batch mode, and it's all autonomous, so you literally hit up, enter. I'll demo this later.
So in developing this tool set, we had to write a couple of custom scripts that aid in debugging some of this information. A lot of it depends on, like I said earlier, you call into a DLL Microsoft provides, RPC-RT4, and inside of that, depending on what kind of data you're unmarshalling, it'll call through different functions. And in order to track it down, we haven't showed an IDL yet, but you will have structures that embed structures with an array of data types. And when you're really deep into a data structure, it's pretty hard to tell which specific point failed. And so to fix some of that, we wrote these scripts that breakpoint on any time RPC raise exception is called, and from there we can trace it back. So we provide a lot of these scripts, not necessarily that they're useful since we've done a lot of that for you, but if you want to go in and take a look, they're kind of interesting. The script hooks those points I mentioned inside of RPC-RT4, RPC raise exception, and a couple of different unmarshalling routines that you can see. And we did our debugging in Windows XP SP2 in 2000, so it'll work in that. We also have some scripts that will pull out the format strings and correlate that between the IDL you saw and the format string, and which function will be called inside of RPC-RT4 to handle that type of data, to unmarshal it. In order to communicate with any of the RPC services, you have to have a pipe name. So we provide a script that will just pull that out. And the way it does that is we do a cross-reference to the use protocol sequence call inside of RPC-RT4. We back-reference that. We trace back up the what would be the stack statically, and we pull out the call for the pipe name. And that provides an easy way for you to open a binary, you're auditing, run this script and have it pull out that pipe so that you can communicate with it with our tools. And Aaron will demo, taking all this information and going from not knowing anything about a service, pulling the pipe name, communicating, and actually calling functions. This is a concept we came up with to help with things like the context handles. Aaron mentioned that a lot of times you have to have a valid context handle before you can even call the rest of the opcodes. So what we want to do is try and use provided symbols to figure out which is going to be the first opcode we may need to call. There's other ways to do this that we actually do. We look for any IDL that may take a context handle as an out parameter, but for certain things we can use a symbol like open printer EX. If we see something like that, we may have a list and realize that if we're going to call anything in the spooler service, we may want to call the ones that will open a printer first. Things like that will help us infer what needs to happen first before we can further audit the rest of the services. And like it says, it allows for better code coverage, allows you to access more of the opcodes you may want to audit or find interesting.
All right, so I'm going to walk through a complete audit from start to finish of a CA product, specifically BrightStore ArcServe Backup, which it's the service that has the 400 opcode interface that I had mentioned earlier. And we actually are going to show a bug that we just found last night. It's probably not exploitable, but there's so many in the service that it really doesn't matter anyway. So Cody will narrate, I guess.
So like we mentioned, this is, what we're trying to provide here is a way to audit these services. RPC does exist, people still use it, there's still bugs. And I think a lot of the problem is that people don't know how to go from point A to point B and don't have all the necessary tools. Tools exist to pull pipe names, tools exist to do the IDL, things of that nature, but there was never a gap to really go from, 0 to auditing quickly. So what we're going to try and do is go through that process, and as a researcher or someone looking for bugs or wanting to test their product can go through quickly and easily. So
the first step we're going to do is I'm going to run that script that I had mentioned earlier that will recursively go through a directory and tell you what imports RPC functions. So assuming you just installed CA BrightStore, you give it the program file directory. This uses PE file by Aero Carrera, and it just checks the imports, finds any RPC services that may be listening. So you can see it's finding ascore.dll and asdbi API, or asdb API.dll. So the next step is we're just going to see if there are any processes running on the system that have named pipes, which there will be. This is just using Process Explorer from sysinternals. If you search for named pipe, you'll notice there's a named pipe named ascore and also one named asdbi, or asdb API, which matches the DLLs and execs that are in the program files directory. So you can safely assume that you can communicate with those services using the name pipe over RPC, and they're handled in those two DLLs.
And using Process Explorer is a real easy way to just verify those DLLs that got pulled out, because you can search by handle name. You can search for all the name pipes on the system as you're already on the system, so you can quickly.
Anyway, so that batch script dumps the IDB and the IDLs for you. This is IDAPRO, and it's just the ASDB API, which we're going to use as the example. If you were to run mIDA in here, you will see that it has these 400 different interfaces.
And each one, this is the IDA plugin that we mentioned. Each one is a function. Each opcode will call into that function, and as he selected one of them, this is exactly where you would hit if your data got unmarshaled, and if everything checked out from the RPC RT4 side, call up to the actual CA binary, the service that they wrote. So, with these tools, we don't, like a developer, we don't really care about the unmarshaling, things of that nature. We shouldn't. We just want to hit each of these RPC functions and do it easily. So
at this point, what we've done is you found the process, you found the name pipe. So if you want to communicate with this, the last bit of information you need is the IDL. So you're going to need to know which opcode you want to call. You're going to need to know the structures and any of the unions, and you need to know how to pack all that data. So for instance, if we want to call opcode hex A, we have the IDL because that script batch generated it. I'll pull it up here. You can see here, it defines a UUID. I don't know if you can read that, but it defines a UUID and it goes through all the different structure elements. So we decided we'll call opcode hex A. So you can see here, this tells you where it's defined in the binary at this address. It takes in a handle T. The handle T argument isn't transmitted over the wire, so we don't actually have to worry about that. Has a conformant varying array of size 256, length 1 element. So it's basically saying that there's a struct 2 as element 2, also has a character string, and 2 shorts and another structure. So normally, if you were to audit this, you would have to pack all this by hand. So you'd have to do all the different sizes and max size and all that kind of thing for the conformance varying array, and you have to get that right. You'd have to then include structure 2, which, as you can see up here, contains a long, a character, array of 16, all these different elements.
Long array. And oftentimes, this example is just really primitive data types, but you could have struct 2 include an array of struct 6s. Struct 6 may have a union that has 30 different cases that you need to actually, for code coverage purposes, call each one. And so our tool set will do all that in a manageable way, as opposed to you having to, and I've done it a million times developing it, had to write all these by hand. Go back to the opcode. If you see a sizes and length is, it's actually an array. And you have to know how to package all that and how to specify the array so that it properly gets sent up to the function you're trying to hit. Strings are the same way. Little bits like handle T not getting transmitted, that's handled by our tool set. You don't have to go research that and figure out exactly what does and does not get transmitted on the wire, which is a big time saver.
And this example it's not the easiest, but it's also not the complex. If you look at some of the Microsoft ones, I mean, these things are obscene. They're thousands of bytes. You'll have 16 structure deep unions and things like that. Just extremely hard to do by hand. And that's just the beauty of the stuff that we've been working on, is you can just point it at it, say, basically click and go.
And this one doesn't have symbols. When we talked about symbol inference, if you have symbols for the DLL or EXE, you may be looking at, it says long sub 28E. This would actually be a symbol name, which is where we get into parsing that and trying to infer some data from it, like OpenPrinter.
So this is the address right here where this opcode is specifically defined in the binary. So we can actually jump to that. You'll see this is where your code should hit if you pass all the marshalling. This is where your execution should end up if you pass all the marshalling problems and you manage to get here. So if you want to audit this, this would be the address you want. So I am going to attach to this process and set a breakpoint on that, so we can see that we actually do unmarshal everything correctly.
You should use the immunity debugger.
See, I would use the immunity debugger, but it's Python 2.5, and that breaks a lot of the stuff that we wrote in 2.4. But now I'm just attaching to the process that defines this name pipe. In a second. I'm just going to set a breakpoint on there and make sure that our data actually gets there. In the meantime, so basically I'm going to use our toolset now, just calling parse test. It's just a little bootstrap program I wrote.
Show them how it showed parse test.
Sure.
Parse test is something that you can use to call. You provide the IDL, like we mentioned. You can provide an opcode just to call one. Don't go too far. And this is how you actually access all these objects inside of Python when you import our lexer, when you import our NDR types. This is how you would use it in a script to talk to some of these services. If you notice, you have IDL equals main file name. That's actually responsible for parsing or lexing an IDL file into all the objects we're going to later use. And it says, for each UUID and IDL. So it's all packaged so that you can loop through it. They're all in list. They're all in list so that you can easily access them. You can call through any of the opcodes you want. You can call through any of the interfaces you want. It provides a real simple way to get at that data. We just have some of this in here left over. You can specify which UUID you may want to hit, send it, or just check out the data. So
now we're attached to the process. Just going to let it go. And I'm going to breakpoint on the handler for opcode 10. So I'm going to run that parse test. I'm going to give it the IDL file, give it the IP address, the pipe name, and the opcode number. So what this is going to do is going to take the IDL. It's going to completely parse the entire thing. and it's going to specifically package opcode 10 and send it over the wire to that IP